Okay, thank you very much. So, merci aux organisateurs. Bon, j'ai pas d'anecdote concernant Denis, contrairement à la plupart des, parce que bon, je le connais depuis qu'il était étudiant en thèse, hein, donc ça fait assez longtemps, mais malheureusement, j'ai jamais, avec une exception, j'ai jamais vraiment travaillé avec lui, sauf sur un papier avec Denis et Antoine Leget, qui a quelques connexions avec ce que je vais raconter là, mais bon, assez lointaines. Okay, so I will speak about systematic jumps, and it's a joint work with two people, Viktor Todorov, who is at Northwestern University, and Willy Lin, who was a student of Todorov, of Viktor, but she now went to the industry, so, okay. So it's a joint work with them. Let me write on this board the setting. So we have capital N assets, and the price of these assets follow the following equation. So xj is this asset, xt, this is the initial value plus the integral of some drift plus the integral with respect to some Brownian motion. Is that large enough? Okay. dwj, okay, winner process, of course, plus jumps, which you can integrate like this. So theta j of S and Z with respect to a, well, Poisson random measure minus its compensator, ds dz, and u, well, it's no restriction to suppose that they all have the same compensator. It's always possible. It's a jump process on R, point process on R plus times R, and you can always suppose that nu is just the product of the Lebesgue measure on R plus times the Lebesgue measure on R. That's not a restriction, and the mu j are independent. So this is the idiosyncratic part. And now you also have k factors. Okay, and those factors are driven by winner processes also, which are independent of the driving terms here, plus possibly jumps. So you will have the integral. So I will forget about the drift in the factors because you can include them here. It doesn't really matter whether you put the drift here or in the factor. It's, okay, so you have the influence of the kth factor is an integral with respect to a Brownian motion, of course. So I will write it like this. So you sum over all factors, dw, well, say, let's tilde that js, okay? And you also have jumps in the factors. And, well, there is a big restriction, is that there are finitely many jumps. Well, over finite time intervals, of course. So it's a rather strong restriction, but not so much in view of, well, concrete data, in fact. And so instead of writing them as the integral with respect to the jumps of the factors, I just write them, so they occur at some stopping times, rho p. So you sum over all jump factors up to time t, of course, and the influence of all factors altogether, because that will play no role afterwards, is just this. Okay, so this is a typical factor model that you would consider. And yeah?
So the Brownian motions W tilde are indexed by J or?
L, sorry, L. excuse me, thank you. Okay, so this is the problem we are looking at is whether we do have some other jumps which are common to some or most of the prices, but not included in the factors. And well, the reason is that, well, in some sense, if everything is continuous, you just forget about the jumps. Well, there are several methods. Well, I'm not so convinced by them, but several methods to establish the number of factors, the minimal number of factors k, and okay, so, and the literature is quite large about that. So here I suppose that for the continuous part, all the influence of the factors is really given by that. And okay, if you have add jumps, you will have that. But the question is, do we have other common jumps, or possibly common jumps? So I will consider another sequence. Again, it's finitely many jumps over finite interval. And so I have another sequence of stopping time. Okay, I will make the precise assumption later on. And the influence and the factor will be, well, the jump of the j's price at, or log price at this time will be delta jp. So again, it's the sum. Okay. So the question is, do we have this term and can we evaluate how big it is in some sense? Okay, so that's the question. And as we won't see here because I have no slide and no, although in the paper there are, of course, empirical applications, but I don't have time anyway. But on the empirical study, actually, yes, the answer is yes. You have this type of terms for if you use typical models that people in finance use. Okay. So what are the assumptions? So, well, on B, sigma, theta, lambda, the assumptions are quite standard. So basically there are two types of assumptions. First of all, well, they should be kind of not too big. So for instance, on B, sigma, and lambda, you will have the supremum over S smaller. So I should say that the time, well, I will erase that. So the time horizon is fixed. So we are on the time interval here. So of course the assumptions concern only what happens up to time t. Afterwards we don't care. Okay, so the supremum of that, say for instance bjs, or lambda, or sigma, or lambda jls, or concerning theta, theta j sz over phi j s, z, where phi j is a function. So of course, well, this stochastic integral should make sense. So theta should be smaller somehow than some function, which is, well, the function of, say, we can z dz. So to some power w, this is, well, say, equal to 1. So you pick functions like this, and w should be, well, between 0 and 2. So that means, so the supremum of those things and the expected value of the supremum taken at any power is finite. Okay? You can localize these assumptions, of course, but that's complicated enough like this. So that's one type of assumption. And the other type of assumption, again on the general coefficients, is that we need some regularity for the lambdas. So the lambdas, basically, lambda j L for any L, in any j. So if you take stopping time, so I take here the supremum when S prime is between 0 and S. Okay, so this goes to 0, and the same if you look at lambda JL, S minus S prime minus the left-hand limits. Because of course, when you have, the left-hand limits, so that means lambda should be cat lag, and well, again, the expected value of this should be smaller than a constant times S to some power rho, which is positive. Okay. So that's a very standard assumption, not quite strong, except that it's uniform in J in some sense. Right? Okay. And for the betas, well, actually, the rho p are any sequence, strictly increasing sequence of stopping times, and beta j, well, there is no measurability assumption, of course, but apart from that, there is no assumption at all on that, because as we will see, we just eliminate the problem immediately, and it doesn't matter. Okay, now, what are the assumptions? Well, I don't need this anymore. And the assumptions on this. Well, first of all, the tau p's should be a Poisson process. Well, the jump times of a Poisson process. Okay. Secondly, conditionally, if you know all tau p, rho p, and well, all the driving terms, wj, w tilde l, okay, and also the lambdas. Okay, conditionally on that, well, the delta j p are IID. Okay, so that's a strong restriction. Okay, well, two strong restrictions here. First of all, that the tau p form a Poisson process, but that's not very strong. Well, you have finitely many of them, jumps, of course. But this is strong, but really what you really need would be a central limit theorem for the delta j when j varies, and when you take the sum, the weighted sums of the delta j over j, and you need a central limit theorem for that. But, well, the weakest possible assumptions are rather difficult to state, so I stick with this very simple case. All right, so I won't use this anymore. And the question is, how do we measure the size of this, or how do we check the presence of such terms? And for this, I use the fact that because those are IIDs, well, if you take any function h with polynomial growth, well, IIDs with moments, sorry, I forgot to say, with moments of all orders. Okay, so, well, order up to 8 would be enough, but okay. So if you take h with any function with polynomial growth, and if you look at the sum of h of this, of course, that converges to something which I will call delta bar for the mean so it's h and p, so it depends on the function and on p, and which is also the expected value of h delta j p conditional on this sigma field. Right? Just by the law of large numbers, okay? And so I will estimate the size of this with the following quantity. So we pick a function, test function g, which I will specify in a moment, and I will look at the sum for all p. Well, of course, all p such that tau p is smaller than capital T, the time horizon, and I consider delta GP squared, in fact. Well, why squared? Because it's just kind of convenient. Okay, and what the function g is, well, it's any test function which is smooth enough, so it should be C3 with bounded second and third derivative, and with g of 0 and g prime of 0 equals 0, right? Okay, so typically g of x is x squared. Well, not necessarily, of course. We also want to estimate, well, have an idea of those jumps when they are positive, for instance, or whether there are such jumps lying in some interval, sub-interval of R. So you take G, well, a smooth version of the indicator function of this interval, for instance, or things of this sort. So we want to estimate this, and also derive test for whether this is positive or not when G is never 0 except at the point 0, of course. Okay, so in fact, well, then things starts now, and it's, I'm very sorry, it's rather complicated. Lot of notations because, well, the problem is that the naive estimators for this quantity have a lot of noise due to the presence of, well, the idiosyncratic part, of course, well, not surprising, but also especially because of this continuous part. Okay, well, the jumps don't play any role, as we will see. Okay, so I will split, well, if you take the function I of x, which is the identity, okay, so this is, well, maybe I should, well, okay, it's I. You can take I here and look at IP. Okay, so this is the average of the jumps. Okay, and there might be two different cases. Either this is 0 or this is not 0. If it is 0, if it's not 0, it means that in some sense, well, things are easy, but it contradicts the fact that, well, among the factors, you typically have the market, the factor, the kind of weighted average of all prices, which are typically one of the factors, or variants about this, because if it's included in the factors, then you should not have this different from 0, right? But nevertheless, the treatment, mathematical treatment of the situation where this is equal to 0 or not 0 is quite different. So I will consider not only this, but say Sj prime, which is the same sum over P, always with this, delta J P squared, indicator delta J I P is equal to 0, and S double prime, the same thing where it's different from 0. All right. Maybe I should. Maybe it's better like this. Okay, so we want to estimate those two things, and well, essentially that, but in practice, we estimate separately those two things. So how do we do? The first thing is to eliminate, well, maybe I should put this up. And, okay, the first thing is to eliminate those jumps. So remember that this is related to the factors, and we observe the prices, and we observe the factors. Well, how do we observe them? Well, on a grid of size n. So we observe at each time I over n t. Okay, so we have n observation. I goes, well, n plus 1 observation. I goes from 0 to n. And, well, my usual notation is saying that delta n is t over n, and delta ni for any process is the increment of the process I delta on the interval, and I is the interval delta n, I minus 1 delta n and I delta n. Okay? So you observe the factors here. So in fact, it's very easy to spot, to figure out in which of those intervals the rho p are jumps of at least one of the factors. So you aggregate all those factors, and it's very easy to find the intervals on which which contains one rho p or not. So I will consider this set I. This is the set of we have an estimate. Well, I should say I is the set where I n I does not contain a rho p. Okay. So it's all of them except finitely many of them, and we have estimators. I will put a hat for all estimators, which depends on small n, maybe capital N, and so on. Find an estimator, well, a subset such that this goes to 1. So there are several standard methods based on truncations or things like that in order to estimate this. So in the sequel, I will not consider the intervals which are indexed by the complement of hat I hat. So only those indexed by I hat. And to avoid, well, notations are complicated enough, so I will suppose in sequel that I hat is just the whole set. You have no, it's like having no jump. So you can forget about that up to notational complications. It's not a problem. Okay. Okay, so what do we do? So we have eliminated this in some sense. And then I erase that because, well, it's like supposing that there is no I. Now, next thing is to estimate the set. Well, there are two sets of interest, in fact, in this thing. The set I prime n. So the interval, I and I contain a tau p with delta bar I. So remember the delta I, which is here, which is equal to 0, and the set A prime n, which is the same thing with different from 0 here. Okay? So you have those two sets. And of course, they are not disjoint because when n is finite, you might have two different tau p's in the same interval or three. Okay. But asymptotically, of course, they are disjoint. Okay. So the first step is to estimate those two sets. Okay. And for this, we use the following thing. Yeah, wow. Sorry, it goes up. No, but that you cannot. Okay, but I suppose I can figure out it. So I will take the average of the prices. Okay. And I will look at a kind of return, the ith return of, well, this is the return of xj, except that I take minus some psi, some number, which is, well, say positive number, and the best choice, but impossible, would be to take psi equal 1, but in practice it should be close to 1, in fact, times the delta. Okay? But now you truncate this when this is smaller than some gamma n, and the gamma n which is here is something which goes to 0. Well, I forgot to say, of course, sorry, that small n goes to infinity, that's clear, and but capital N also goes to infinity, and so this should go to 0 when, okay, but gamma n squared times the infimum times n to, so this should go to infinity for some epsilon, which is positive. Okay? So you take a truncation. So that means here you just kill the, well, somehow the continuous part. No, not quite, of course, but it's a kind of thing that we are doing. And if you take for any function j, then you will take ag of sorry, I is the sum of g of this return, truncated return, and you do that, and okay, and so what is the estimator? Well, for, sorry, this should be double prime. Okay, so the estimator for double is just the set of all I such that, well, delta n I x n, so the average, right? Because this is, you can say, this is the part where the average of the deltas is non-zero. So that should mean that the average of the increment should be large enough. So when this is bigger than gamma n, well, you can take actually the square root of this, okay? And for, so that's very simple. And for the other one, this is a set I such that a hat g of I minus a hat g of I minus 1, 1/2 minus 1/2 of a hat g of I plus 1. So you have to be careful, well, for the first interval and for second interval, the last one, you don't have I minus 1 or I plus 1, but for all the others you do, and which is bigger than gamma n times some quantity, which is the sum of the same thing as A, but truncated. So if I put here, I additionally say that Rj is smaller than the gamma, the same gamma n here. I will put a t here for truncation, and this is smaller than the sum over all I of the, again, this A truncated minus I minus 1 minus I plus 1 truncated. Okay, okay, take the absolute value of this. Okay, and okay, that's a bit complicated, and I should hurry up because time is going. But what we can prove is that the probability that I hat prime is equal to in goes to 1, and the same with double prime. Okay, so now let me T1. Yeah. Yeah, okay. Okay, so, well, so now, what are the estimators? Well, the first estimator, so we fix some G, properties. The first estimator, the most naive estimator would be just the sum of the A hat J of N, I squared. Okay. The second estimator is the sum of basically the same thing, except that we take the difference. We take differences. Okay. Well, okay. Well, 1/2 of that. And the third estimator, which is the best one, is S prime J plus S double prime J, where S prime J is only, so you take advantage of the estimators hat I prime or double prime, saying you take the sum, but only for those points where you know that you have a jump. Okay? And if you want to put double prime here, you put double prime here, and you take the sum. And all three satisfy the same central limit theorem with the rate of convergence, which is square root of this. Okay? And, well, I don't really have time. Well, no, I don't have time. I should stop now, right? Well, I have two minutes. Okay, but still. Still, so you have this, that S at J minus Sj converge in law. Well, it's converged stably, conditionally, well, stably, but not with respect to the whole sigma field, but with respect to the sigma field, which I've erased, of course, but with respect to the conditioning sigma field I had at the beginning. Okay? And this converges to some complicated limit, which depends, well, this is under the assumption that n, small n over big N, goes to some limit phi, which is in 0 infinity. So it could be 0, it could be infinite, or anything in between. So that's the nice thing about that, that we don't suppose that the frequency of observation is much higher than the number of n, or much smaller. It could be one or the other, or anything in between. And so, according to phi, when phi is equal to 0, it means small n is small with respect to big N. So the driving term here is in fact a function of the lambdas which are here, except that since lambda can jump, it's a bit complicated. It's not Gaussian, but it's a kind of sum of variable gamma plus z plus I, well, p, sorry, for some times kappa p plus gamma minus p, z minus p, 1 over kappa p. where the kappa p is uniform over 0, 1, and the z plus and z minus are Gaussian. And okay, so this is leading term. On the other way, if phi is equal to infinity, so, well, the driving term in the central limit theorem is due to the central limit theorem for the delta j, p. So you have a term which involves well, the variance of this thing, and otherwise it's a mixture of the two things. So, but so this is in fact when say 1 over supremum of phi, well, square root of phi here, okay, plus a term which is 1 minimum phi times something which relates to the variance of the delta p. Okay, so when phi is 0 or phi is infinity, one term is missing. And in practice, well, the tree satisfies the same central limit theorem, but if you try to look at the bias, well, of course, it's impossible in general, but in the case you don't have jumps, well, systematic jumps, then, of course, this, it means well, those things are empty, so this is a perfect estimator. Well, this is 0, so it's perfect estimator of 0. And you can look at this, and those two things converge to 0 at the rate n infimum n, which is, of course, much faster than this, but still. And the limit of this is much bigger than this. So this is the worst estimator, this is a bit better, and this is much better. So you have that, and so I'm very sorry because I didn't, well, but I cannot really go to the end, but based on that, it's possible to have estimators because of stable convergence. If you have consistent estimators for these quantities which come here and also here, well, you can derive, well, confidence interval, a rather standard way, except that this is not Gaussian, of course, because of the presence of this uniform variable. But still, it's possible to do this. And you can also derive tests for whether this is well, this is 0 or not, so I don't have time for this, but well, if somebody is interested, there is a paper which is even more complicated because I didn't went into details, but anyway, apart from that, the proofs are rather standard. It's a bit complicated, but quite standard central limit theorem and such things. Okay, and the vague connection with what I did a long time ago, well, 15 years ago or more than that, with Denis and Antoine, is that we looked at the case where you have no jumps and no idiosyncratic part, and we establish we try to see K, which means finding the biggest the biggest possible rank of the diffusion matrix as the time varies. So it's smaller, of course, than big N, but okay, so this somehow loose connection. Okay, well, sorry for this messy talk, and thank you very much for your attention.